to where she'll be appreciated. All right. Okay, so we almost are done with our whole discussion of cellular respiration until we go into cellular respiration in more detail. We need to talk about fermentation, and as we do that, we actually need to take a step back, and this is going to be weird because when we talk about fermentation, we have to start our discussion of fermentation with a discussion of glycolysis. Okay? And so somebody, well that's a Y, somebody remind me what the products of glycolysis are. What are our products of glycolysis? Katie.
2 ATP.
2 ATP.
2 ATP.
Sure.
2 NADH.
2 NADH.
2 pyruvate.
And 2 pyruvate. Okay, so these are products of glycolysis, are they not?
I believe so.
Yes.
Aerobic and anaerobic, but we probably put our products for them under the aerobic list.
I put them under both.
Okay, that's fine. So building up ATP is not a problem because we know that the cells make and break 100 pounds of ATP every day, right? So we're not going to worry about building up excess ATP. Okay? Building up excess NADH, that's not really a problem either because on Thursday we saw what happens to NADH, right?
Right.
What does it do?
It
gives its electrons and its hydrogen to the electron transport chain, right? Only in the presence of oxygen though, right? That's if you can do aerobic respiration. And so now this is a little bit interesting because in order to make NADH, what did we need? In glycolysis, what do you need to make NADH? Nope, but the NAD. So let's do this real quick. I want to show you this reaction. We saw this before. I don't know if you wrote it down or not. So we've got NAD plus plus H plus 2 electrons gives us NADH.
Well, yeah.
Okay? Right?
Right.
Do you remember this?
Makes sense.
Maybe? Okay, so we've got NAD plus a hydrogen ion plus 2 electrons gives us NADH. So what do we need to make NADH? We need NAD plus, and then we need these that are actually going to come from our fuel, from our glucose or whatever that fuel is. That's what's going to give us the hydrogen ion and our 2 electrons. Okay? But we need NAD plus, which is not a problem if you can do aerobic respiration because NADH goes and gives its hydrogen and its electrons to the electron transport chain, right? And then it restores NAD plus that can be reused in glycolysis, right?
It's a whole process.
Does that make sense? Do you remember that?
So does it kind of like recycle it, I guess?
It does, absolutely. So it can be reused in further rounds of respiration.
That's pretty good.
Okay, you like that? Also, we're building up pyruvate, which in aerobic respiration is not a problem because then what happens to pyruvate? Somebody remind me from Thursday, what happens to pyruvate following glycolysis in aerobic respiration? Kyle. Pyruvate oxidation, where you take some electrons away from pyruvate and you form acetyl-CoA, right? We've got a 3-part reaction. Well, yeah, because we start with 2 pyruvate, and so we form 2 acetyl-CoA. 1 acetyl-CoA for every 1 pyruvate, but since we're starting with 2, we get 2 of them.
That makes sense.
Okay? So we have a 3-part reaction that converts pyruvate into acetyl-CoA, right?
Yeah.
And carbon dioxide, which then, leaves the cell and gets expired. Okay, so pyruvate doesn't build up in aerobic respiration. It gets converted into something else that then goes into the Krebs cycle. Right? Is it coming back?
Yeah.
Oh, it will. It will.
I'm reading my notes.
Okay, but
Engulfing.
if we can't do aerobic respiration, we need to assure that we're not going to build up an excess amount of pyruvate and we're not going to build up an excess amount of NADH. We need to restore our NAD+, and we need to figure out something to do with this pyruvate. Otherwise, you're just going to keep going through glycolysis, making more and more and more and more pyruvate, and that's, I mean, you don't want that, okay?
What would happen?
What would happen? If pyruvate continued to accumulate and the cell had no way to get rid of it, I mean, it would just create toxic conditions where there wouldn't be enough space for the cell to do other things that it needed to do. Alright, so let me erase this. And so here's where fermentation comes in. And that's why, yeah.
Well, it's off topic, so I wait.
Yeah, just wait a moment. So in anaerobic respiration, it can't stop with glycolysis because we need to restore NAD+, and we need to get rid of this excess pyruvate. Okay? And so you have two different types of fermentation. There are actually more than two, but they're the two main types of fermentation. One that happens in our cells and many eukaryotic cells, and that's this one. Pyruvate gets converted into lactate or lactic acid, and as it does, you actually take NADH, and in part of this reaction, NADH is converted into NAD plus hydrogen ions.
Like half a page.
Is this a part of pyruvate oxidation, or is it?
This is completely separate. This is fermentation. Yep. This is all under fermentation. See the ferm here? That's short for fermentation.
You know?
Okay? Fermentation. Now what else did NADH have in it other than this hydrogen ion? 2 electrons, right? Where did those go? Yeah, they went into pyruvate to convert it into a different chemical altogether, into lactate or lactic acid. Sorry, if we do lactate, the hydrogen's actually here. If it's lactic acid, the hydrogen is free, but the hydrogen's mostly free. Okay? Alright, so pyruvate, NADH, we've restored our NAD+ that you need for glycolysis to work, and we figured out something to do with this excess pyruvate. And then lactate or lactic acid can diffuse out of the cell, which in the form of lactic acid will make your blood pH lower, create those nice burns that you associate with, you know, straining your muscles more than normal. Do you ever wonder why you stop becoming sore after you keep doing the same thing repeatedly? Yeah, Ray.
Hydration.
Well, that's part of it. If you are really, really well hydrated, you can eliminate some of that.
Yeah.
But you just your body becomes more efficient at running blood through those tissues that are regularly carrying out anaerobic respiration. Okay? So this is one form of fermentation. Okay? That's one form. Notice something we did not produce in this form. So when we go through and you look at that original reaction for cellular respiration, it was this. C6, H12, O6, plus O2 to produce CO2 and water, right? It's a combustion reaction. Notice if we don't have oxygen present, we cannot carry out this reaction. Okay? So we're still doing anaerobic respiration, but we are not carrying out this reaction, so we are not going to make water, we are not going to make carbon dioxide. Because there's no oxygen present, so we cannot carry out that reaction. So the pyruvate we make, rather than going and producing carbon dioxide and ultimately producing water if it makes it to the electron transport chain, pyruvate gets converted into lactate or lactic acid, and that's it. Yeah.
Would you say there's a difference between lactate and lactic acid?
Whether or not there's a hydrogen on an OH group.
And lactate has the hydrogen on the OH group, or does not?
Lactate has the hydrogen on it. Lactic acid has lost that hydrogen. Yeah. They're chemically very, very similar. Alright? Does this make sense? Okay, so this is the type of fermentation that happens in our tissues. This is the type of fermentation that happens in yeast and most bacteria. So let's do this. This is us. And we'll put this one, we'll just put yeast. So this is what happens in our cells. This is what happens in yeast and some bacteria. So we've got pyruvate. We have one reaction to get it to acetaldehyde. Sometimes this is dropped, this YL is dropped to make it an easier word to say. Acetaldehyde. And then there's a second reaction where NADH is restored into NAD plus and hydrogen ions, and then we make ethanol. Not we. Okay, so bless you. Here's a second fermentation reaction. It still accomplished the same thing. It did something with the excess pyruvate, right? Did it do something with the excess pyruvate?
Yeah.
Sure did.
Into something.
And did it restore NAD plus because you need that in glycolysis? Yes.
Correct.
Wow. This is rough. I know it's Monday and it's rainy and dark. It still feels like you should be sleeping.
It feels
That should always be said.
feels like it's
No matter the time, no matter the place. If you know yourself.
Okay? This is it for fermentation, unless you all have some questions. But you see, we've gotten rid of our excess pyruvate that we make during glycolysis, and we've restored NAD+, Trinity.
So it's like when you do fermentation, does that get rid of electrons?
It does, yep. So these, right, the electrons from NADH are going into acetaldehyde or acetaldehyde to form ethanol. So ethanol would take on those electrons. So then this one, if it's losing electrons, what's happening to it? Is it being oxidized or reduced? Oxidized, right? Oxidation is loss, oil rig. And then what's being reduced? The acetaldehyde is being reduced into ethanol.
You're right.
So
I am right.
I would agree with that statement.
Yeah.
That's giving its electrons to ethanol.
No, NADH is giving its electrons to acetaldehyde to form ethanol.
That's what that arrow means.
Yes. Well, this arrow is showing that there's a side reaction. So one part of the reaction is acetaldehyde becoming ethanol. Another part of that reaction is NADH becoming NAD+.
Wait, can you say how you say that in the middle again?
Acetaldehyde. And again, sometimes you'll see this YL dropped and it'll be acetaldehyde or acetaldehyde. But I don't like that. So I gave you all the letters. I don't want to abbreviate here.
Can't have it.
Alright? Why is it good that this is not the type of fermentation we do?
Because it's. Yeah, we don't need all that.
Because ethanol's bad.
Well, because if you were sprinting and you're using a lot of anaerobic respiration, you would, all of those cells going through anaerobic respiration without oxygen would be making ethanol. And at the end of your sprint, you would have a very difficult time standing or walking or staying awake or living. Yeah, I mean, if you tried to run a marathon, you would for sure die of alcohol poisoning.
Alcohol?
Oh,
So
yeah.
you get like, because you like actually.
You're gonna
Yeah.
die anyway.
Your blood alcohol content would be way, you're going to die anyways at the end of a marathon. Did you ever read about gosh, I don't know if you guys are old enough to remember this, because this was probably 8 years ago. Somewhere between 8 and 10 years ago, there was somebody that ran a marathon every day for a month.
How?
It's healthy.
So he ran 30 straight marathons. I don't know.
Was he like just like?
So why do people get on a sailboat and try to circumnavigate the world? Right? I don't know. I don't know. Okay, are there any questions about fermentation?
But it provides so much less energy to be in a flow.
Oh, have you ever sailed by yourself in a small sailboat?
No, that's so
It
sad.
is very, very difficult. Unless you've got like a nice consistent wind, it is a ton of work. Probably not as much work as running a marathon. Alright? May I erase this? Sweet. Fermentation gone.
Bye-bye.
Bye-bye. Alright, all of this. Gosh,
That was fun.
this is good stuff. I hope that if nothing else, you remember this, right? I don't really care whether or not you appreciate it or you enjoy it, but I just hope you remember it.
I'll try my best now.
Have you ever sat down and wondered how many people have you on their list of like the 10 worst people in their lives?
I've thought of it the other way, but I've never thought of it the worst.
You make the best.
Yeah.
Oh, I don't even care about that. I want to know. I spend hours trying to make a list of all the people that I'm pretty sure I'm on their top 10 worst people in their lives.
I think I have like this.
Those are good days. Those are good days that start off that way. All right, so alternative fuel. All right, let's figure out what we do with this alternative fuel thing. Okay, so somebody remind me the 3 main steps of aerobic respiration. Glycolysis, right? So glycolysis, we go from glucose, typically, okay, right? We go from glucose, and then in the first steps 1 through 5, we generate 2 G3P, wonderful. And then in steps 6 through 10, we generate 2 pyruvate,
I remember writing this. Where did I write that?
right?
Partial oxidation of sugar.
Yeah.
Yeah.
And lost electrons.
So here's glycolysis, right?
Right.
Okay? And then we've got pyruvate oxidation, where we take pyruvate and in a 3-part reaction, or in 3 reactions, we generate 2 acetyl-CoA. Right? And then we do the Krebs cycle,
4 CO2. CO2.
and ultimately at the end of the Krebs cycle, we want to account for all of our carbons. So let's say plus CO2 here. We want to account for all of our carbons. So we took a 6-carbon molecule, we generate 2 3-carbon molecules. We're still counting for all 6, right?
Wait, 2? Yes.
2 times 3 is 6. We start with 6, we end with 6, right?
Wow.
It's just beautiful. And then we go from 2 3-carbon molecules to 2 2-carbon molecules. Well, we lost 2, and we lost them as carbon dioxide, right? One of our products of aerobic respiration, right?
Right.
Awesome. And then we go through the Krebs cycle. So this arrow right here represents Krebs, right? And at the end of Krebs, we're not accounting for like our electrons, our hydrogens, our ATP. We're just accounting for carbons. Okay? So at the end of the Krebs cycle, we generate 4 more carbon dioxide molecules. Okay? And now we've accounted for all of our carbons. And you're like, okay, I got this. Dr. Ingo, I don't love it. I thought I would hate it, but I really don't. You did a wonderful job, Dr. Ingle. Not Dob. You did a wonderful job of making me not hate it. I wanted to. I woke up this morning telling myself I was going to hate it, but I don't. And I know where all the carbons go. Yeah, Trinity. Okay, Okay, oh, you gotta save that, and Trinity's got an, or Trinity, you are Trinity. Tori's got an off-topic question as well. Did you forget
yes.
it? Hang on, just one moment.
Oh, okay.
Just one moment, okay? So do you see we've traced all of our carbons? Okay, now we have to start asking the question, what if our fuel is not glucose? Alright, Tori, off-topic question.
Okay, so how do like brain tumors and like aneurysms form?
Well, aneurysms and brain tumors are two completely different things. So an
Yeah.
aneurysm is a bleed, a brain bleed, typically, and so that forms when you rupture a vessel, which can happen a number of ways. It can happen somewhat spontaneously if your vessel just ruptures under the typical pressure that it experiences, or it could happen as a result of trauma. Like if you take a shot to the head, it could create enough additional pressure to blow out a vessel. In the same way, like if you get a bruise taking a shot to the arm, similar idea, except for it's happening in your brain rather than just in your muscle somewhere. A tumor happens as a result of uncontrolled cell growth. And so cells have several checkpoints against uncontrolled growth. And so if they lose those checkpoints, they will start to grow like crazy. And so if it's benign, those cells, they're growing like crazy, but they're all still well attached together. They're not mobile, they're not moving, but if it's cancerous, the cells, not only are they growing out of control, but they're losing the ability to remain attached to other cells, and then they start to travel. And then if they start to travel, they'll wherever they end up, they'll keep their uncontrolled cell growth and start putting enormous pressure on other tissues. And then Trinity, you had an off-topic question.
Why do our eyes water when we yawn?
Why do our eyes water when we yawn? My guess is because when you yawn, you don't blink, and so it delays it. Yawns are not real quick.
Did it work?
But also when you yawn,
I like squint like
yeah, when you yawn, you change the amount of pressure inside of your sinus cavities, and so when you, as a result of changing that pressure, it may just lead to your tear ducts releasing their fluid. I don't know. Yeah, Emma.
Okay, I have two questions.
Okay.
So
Are they off topic?
One's pertaining to Tori and one's pertaining to
Okay.
Okay, so are benign tumors like the same thing, like rapid growth of cells?
Yes.
Like why does that happen just randomly?
Yeah, because the cells lose their checkpoints against that. I mean, every cell is, well, not every cell, virtually every cell is fully capable of making copies of itself, of moving into the cell cycle, but there are checkpoints that keep it in arrested growth. And so if it loses those checkpoints, it will start to go through the cell cycle and start making copies of itself.
And then why are yawns contagious? Like why do
It's psychological. I mean, it's just you see somebody yawning and then your brain. So a lot of times, if you're the first one to yawn as a result of there being a pressure buildup in your sinuses.
You don't yawn if you're tired.
Well, when you're tired, those pressure issues become more common. But it's psychological. So when you see somebody yawning, your brain assumes that there's a pressure problem, and then so it goes to relieve that
Wait,
pressure.
so when I yawn, I have a pressure problem in my brain?
Yeah.
No, not in your brain, in your sinuses, like your inner ear and your nasal cavities, your sinuses here.
So if you just hold in the yawn, will you pop?
You probably your ears will pop. You know how sometimes your ears will pop when you like climb an elevation and then immediately drop again? Yeah, so if you don't if you suppress your yawn, it'll pop that way, that pressure will leave there.
Why are yawns contagious?
Yeah, that's the thing. Emma will give you the answer to that. Alright. So we've traced all of our carbons, right? Now the question is, well, what if our fuel is a different type of sugar? Okay? What if our fuel is not glucose, but it's fructose, or galactose, or maltose? Okay? And so here's what happens. If the fuel is another type of sugar, either the sugar gets converted into glucose, or the sugar inserts in one of these 5 steps And you'll see as we go in more detail which sugar might do that.
That might
Okay.
be what?
That might just enter into one of these 5 steps.
Fructose, because it sounds a lot like glucose.
Fructose is the sugar that enters in here because we'll see fructose will actually show up in these. We're not going to be satisfied. You're not going to be satisfied to just write 1 through 5. You're going to want to write all those reactions out, know what enzyme catalyzes it, what it starts as.
The 1 through 5 satisfied.
No,
I concur.
see, but you think that now when you don't have all the details. But it's one of those things where it's like, listen, believe it or not, cell phones have not always existed.
What?
I know, it's crazy.
No way.
I remember vividly what life was like as a teenager without a cell phone. Okay? And it was awesome. I mean, it was awesome.
How did you
And I lived perfectly. You didn't, and that's what made it so great.
I love that.
That's what made it so. The fact is, in the middle of the day, if somebody wanted to get a hold of you, they literally could not do it unless they went and found you. I know, it was so. It was. What's the term I'm looking for? It was freeing. It was liberating. Right? If somebody wanted to find me,
They'd like ring you and you
When no one-
if somebody wanted to find me, they literally had to go and look for me and start asking people, hey, have you seen a massive redheaded guy? Because I need him. Like, they couldn't just call me on the phone. But anyways, so it's like, I know what it was like to live without it, and I could do it, but now that I have it, it's kind of awesome too, right? It's like, I wonder how I make this right now, and I could literally look it up on my phone, get myself a nice recipe, and make myself something delicious, you know?
That means you were like a young adult when pagers came out.
Yeah, but nobody had pagers were lame. Nobody had a pager unless you absolutely had to have it for your job. Yeah, but nobody was like, it wasn't like, oh, the cool kids have pagers, you know? But you could actually send messages on pagers. Like, you could kind of send something equivalent to a text, but nobody really had them because they were just lame.
My dad got into
All right. Okay, so other sugars. I know you were wondering, like, what about if the sugar isn't glucose? They either need to be converted into glucose, or they have to enter into one of the other steps. And what are some other fuels we could use? You got to think back.
What do you mean? Salt? No.
So you got to think back to our chapter when we talked about our different biomolecules, right? We talked about sugars, and we talked about proteins, and we talked about lipids, and we talked about nucleic acids, and we said that all of them can be used for fuel.
Yeah.
They can all be used for fuel.
Protein, especially.
Yeah, proteins especially. So let's say, okay, well, how do proteins get involved in this process? How do proteins get involved in this process? I'm glad you asked. And there are basically 3 ways in which an amino acid can enter into this cycle. Now, what's our formula for a typical amino acid?
It's gonna need hydrogen. Oh, yeah.
Say it.
Right? This is what an amino acid looks like.
Yeah.
Okay?
Is that a question?
How many carbon? No, it's not. I mean, it's a rhetorical question. I mean, this is what an amino acid looks like. How many carbons are in this?
Dos.
2. Where do we have a 2-carbon molecule in here?
Dos.
Right here. Acetyl-CoA is a 2-carbon molecule, is it not?
It is.
So most of our amino acids will get converted into acetyl-CoA. Most of our amino acids will get converted into acetyl-CoA.
Wait, so it just like skips all those other steps?
It does, absolutely. You don't have to do glycolysis. You can do something as an alternative to pyruvate oxidation, and then do the Krebs cycle on the electron transport chain. This amino acid is going to get converted into acetyl-CoA. That's what's going on here.
So what about the protein? What about the protein?
Well, proteins are made up of amino acids. So every protein can be broken down into individual amino acids. But what about this?
Oh shoot.
Think about this one. What if this R group contains some additional carbons.
Then it's
Now there are some alternative places where protein can show up. So I'm going to do dotted lines here. These are minor. Okay? Minor meaning what? Not that they're not important. Maybe that was the wrong term to use, minor, but that they're not common. Okay? And so it can show up here. Okay? If that R group contains some additional carbons, so let me write that. If R has C's. Look at that. If R has carbons. That's good stuff, right?
That is good stuff.
And then there's one other place.
If R has carbon.
Is proteins can end up inserting themselves somewhere in that Krebs cycle. Again, only if R has C's.
What do you mean by that?
If that R group contains some carbons.
So like there has to be a C off of the R.
Yes, at least one.
But there's one, so there must be.
Right, because if you only have two, the only way you can pipe this in is into acetyl-CoA. That's our only 2 carbon molecule in this whole process.
Another C off.
Yes.
Because R's are
Yep. So the overwhelming majority of amino acids, when you, I don't know if you knew this or not, but during periods of starvation, you will start hydrolyzing proteins in your body. That's why your muscle mass is one of the first things to deteriorate during periods of starvation, because it's a great fuel source. Your body will start hydrolyzing those proteins. What's that? Yes, your body starts to eat itself. So really, we're all cannibals, right?
That's disgusting.
Nick liked that. He gave a high five in response to that. Do you even know what I said before you high fived?
Been waiting for this
I
day.
know.
yeah.
I said we're all cannibals.
Oh yeah.
Yeah. All right. What about this? What is the most common way that our bodies store excess fuel? Fat. Man, I didn't even have to use myself as an illustration. I was fully prepared to do that. I didn't even have to. Okay. So typically our body stores excess fuel as triglycerides. Okay, triglycerides. So we'll call this fat. And look at this. You're gonna like this. We've got a glycerol, which is a 3-carbon. It's a 3-carbon part. And then we have these long fatty acid tails. Okay?
Is that what we all have?
Yes.
That's so weird.
So these are called triglycerides. Tri meaning what? 3. Glyceride referring to this glycerol backbone here. So these are long chains of carbon and hydrogen. Okay, I'm saying that in the recording. I'm not writing it. You're going to know it, right? You're going to remember it. These, just like the tails in our phospholipids, you know, our phospholipid tails, and we say that they're nonpolar, and the reason they're nonpolar is because they contain entirely carbon and hydrogen that share their electrons evenly, right? They're good sharers. Okay? So now we've got a lot of carbons. What's in here? A lot of carbons, okay? And so check this out. The glycerol backbone can enter in right here, can get converted into G3P, which is another 3-carbon molecule. Okay, so the glycerol enters into G3P, and then the fatty acid tails, they get converted into acetyl-CoA, 2 carbons at a time.
2 carbons. I did that.
2, 3.
So let's say this fatty acid tail is 100 carbons in length. You're like, man, that's a really long tail. It is. It's so beautiful. So if this fatty acid tail is 100 carbons in length, how many acetyl-CoA molecules can we make? 50.
Ooh,
How many acetyl-CoAs do we make from 1 molecule of glucose? 2. This is an enormous amount of energy. which is why of all of our biomolecules, which biomolecule type contains the highest number of calories per gram? Fat. Almost 20 calories per gram of fat. I think it's like 19.5 calories for every 1 gram of fat. It just it packs a punch. It packs a punch because every 2 carbons off of one of these fatty acid tails can come in as an acetyl-CoA and then go into the Krebs cycle and do some wonderful things. Okay? And so this is why fat is such a great way to store energy, because it's really energy dense. And it's also why that if you're stranded somewhere, you want, first of all, if you know you're going to be stranded, absolutely you want to pack on some pounds to prepare for that. That's why bears put on so much weight in the fall.
You don't know if you're stranded.
Do you know almost every bear that gets hit by a car or mauls a person or eats somebody's dog, it's almost always in the fall when it's putting on enormous amounts of weight in preparation for hibernation.
By a car?
Yeah.
Yeah,
Bears get hit by cars all the time.
You said that's how
There's no bear.
I mean,
No, but they have to put on a bunch of fat in the fall. So they're moving. They're moving around looking for lots of food.
Never mind.
The moral of the story is, if you really want to put on weight, cross roads carefully. Right? That's what it all boils down to. Okay? Any questions about this?
it's a lot.
Okay. It is a lot. There's only one more thing I want to say. We'll talk about this more later. But I want to remind you that there are 2 cells in our body, 2 cell types, not 2 total cells. 2 cell types in our body that they can only use glucose for fuel. None of these other fuels are available. Okay? And what are they? Neurons and red blood cells. True or false? Neurons are important.
True.
True or false? Red blood cells are important.
True.
Now you got an issue, because if they can only use glucose and you are not presently consuming glucose, you've got a problem, right? So your body can't just start taking away your fat layers and feeding your neurons and your red blood cells. It actually has to convert fat or protein into glucose.
But it's not. So, if you're just entering it below, so like you're taking the 3 C's and you're putting it into the 2G3P.
Yeah, but you can't, because they don't have any of the enzymes necessary to carry that out.
So, but I thought you were just entering it right away. Like you have to turn it to.
Yeah, you've got to convert it into that. Yeah, all of these arrows, you see all these arrows coming from the side? Do you see them? Do you see them? You see those arrows? All of those require a chemical transformation to make it into whatever that is in the process. So if an amino acid is going to enter in here, it has to be chemically converted into acetyl-CoA. And there has to be an enzyme to facilitate that reaction. Yeah. And so red blood cells don't have the enzymes necessary to do this, to use other fuel. Okay? Neurons don't have the enzymes to do this. So they rely on other cells to do something really cool for them, and it's called gluconeogenesis. And it's taking something and converting it into glucose. Gluconeogenesis. That's bonus information. Free of charge. Alright? Any questions about alternative fuels? Do you have all this written down?
Yeah.
Yeah, you love it, right? We haven't even got to the 2.0 yet.
Oh my.
I know. We've got plenty of time. We're about halfway through our class. Katie.
What does it mean 3 carbons at a time? What is
Oh yeah, so if this is 100 carbons long, you have to break 2 off at a time in order to convert it into acetyl-CoA.
Aren't they hydrogen tails?
This? No, carbon and hydrogen. Yep. I don't think so. Carbon and hydrogen.
No, what happens to the hydrogen?
Oh, what happens to the hydrogen? Oh, acetyl-CoA has hydrogens in it.
So they don't need that. What?
Well, the hydrogens are part of the chemistry as well, but we're just tracing it as far as the carbons because those provide the backbone. But yeah, the hydrogens are absolutely part of the chemistry as
So
well.
that means 2 carbons transfer into 1 CO.
2 carbons are converted into 1 molecule of acetyl-CoA. Yep. Just in the same way 1 amino acid is converted into 1 molecule of acetyl-CoA. Wow. I don't think disappointing is the right word, but it's getting close. It's getting close. Alright, so I'm going to pause this. We're going to take a 3-minute break. Alright. Have any of you listened to any of the most recent recordings?
Yeah.
Because I've been just doing a white background for the video to try to make it as unbelievably boring as possible. And you're like, Dr. Engel, like, why do you have to try? It's already unbelievably boring, right?
What do you mean?
Okay, so here is glycolysis 2.0. Which reactions are over here on the left?
1 through 5.
1 through 5, how do you know?
Because it's glucose to 2G.
It's starting with glucose and it's ending with 2G3P. Now, for your sake, I'm just going to give you the abbreviations. It's also for my sake because they're really long words and I'm going to spell them wrong. But so in reactions 1 through 5, we are going from glucose to 2 molecules of G3P. And if you remember back to Thursday, you'll remember that to get through these 5 reactions actually requires 2 ATP to be invested. So at the end of here, we are at negative 2 ATP. At the end of these 5 reactions, we are at negative 2 ATP. And you're like, oh no, that's terrible.
It's okay.
We're in the negative. But the thing is, the cell is making and breaking 100 pounds of it every day. So there's ATP to go around. But at this point, you have invested 2. You haven't gotten anything out.
Where do you get negative 2 ATP?
Because I'm going to show you. I'm glad you asked. The first. So I just want you to know that as we go through these reactions, you should be expecting to spend. Remember, ATP is the energy currency of the cell. As we go through these 5 reactions, you should be expecting to see the cell spend 2 ATP. Okay? It hasn't been paid yet, but it's paid something.
The 6 through 10.
Paying it forward.
The 6 through 10 is
Plus 2 ATP.
plus 4 for a net of 2. So in 6 through 10, we have plus 4 ATP. And so negative 2 plus 4 is what? Somebody please give me that. 2. 3.
Guys, we're math pros.
Woo! Alright. So step 1. Step 1. We start with what? Glucose. After step 1, we now have what's called glucose 6-phosphate. Glucose 6-phosphate. What's the difference? They both say glucose, do they not?
But they have the 6 and a phosphate.
But carbon number 6 on our glucose molecule now has a phosphate group attached to it. Hey, where on earth could we get a phosphate?
Phosphate
From
group.
a phosphate.
Yes, you could get it from an inorganic phosphate, or you can get it from the energy currency of the cell,
Oh my gosh.
right?
That's phosphate.
You discovered.
What's the energy currency of the cell? ATP. So here's step 1. Here's step 1, and here we require 1 ATP. The cell is spending 1 molecule of ATP to carry out this reaction.
So it's already losing 1.
It's already losing 1. Of the 2 we know it's going to lose. So that first one it loses is at step 1. And this is carried out by an enzyme called hexokinase. Now, anytime you see this ending here, I want you to think something. Whenever you see kinase, kinase is the name of an enzyme that transfers a phosphate group, typically from ATP to something else. That's what kinase enzymes do. They transfer a phosphate group. Did a phosphate group get transferred here? You bet it did. From where? From ATP to glucose.
Transfer.
Yeah. That's what kinase enzymes do. Do you love it?
Field.
So here's step 1, and we know where we've spent 1 ATP. Right?
Right.
Yeah.
Step 2, we're going to go from glucose 6-phosphate to fructose 6-phosphate. And as we look at this, I'm going to ask you a question. Which sugar do you think can enter the process here?
Fructose.
Fructose.
Really?
Yes!
Phosphate.
Because look at here, it does not have to be converted into glucose because fructose is already part of the party. But here, we need an enzyme that can convert glucose into fructose. So we're not going to spend another ATP here, and this is going to be carried out by an enzyme called this. Kinase. No, it's not a kinase because kinase transfer a phosphate group. There's no phosphate group transferring here. Phosphoglucomutase.
Oh, I don't like that.
Because look at this. We've changed, which is what mutate means, right? We've changed a phosphogluco molecule. Whoa! Do you see that?
Should it be glucophosphate? Because it's like glucose first, then phosphate.
Glucophosphatase.
Yeah.
Mutase.
Mutase.
This is good stuff. Okay. Now we've done 2 steps of the 10. You're like, we're only 20% done, and I'm already just thrilled. Okay. Step 3. We go from fructose 6-phosphate to check this name out. Fructose 1,6-bisphosphate.
Biz.
Oh,
Bisphosphate.
Oh. Yeah.
It's like ice.
Pretty much.
This is like
Organic.
a seizure.
Yeah.
And then are we going to lose another?
Wait, hang on. Just hang on a minute. We've now got not 6, but 1 and 6.
Oh, shit.
And we don't just have phosphate, we have bisphosphate. What does this root mean?
2.
2. What does 1 and 6 mean? It means now there's a phosphate group on carbon 1 and on carbon 6. Where did we get a phosphate group? An extra one. From ATP. There's the other ATP we have to spend. So we got to spend an ATP in step 1. We've got to spend an ATP in step 2. Now we have still a 6-carbon sugar, and now it's got a phosphate group on carbon 1 and on carbon 2.
Wow.
Yep.
Feeling good?
I feel incredible. But I'm going to feel even better when I give you the name of this enzyme.
Oh, me too.
Oh my goodness, this is so crazy.
This is called phosphofructokinase.
Oh shit, it's already done. Glucose.
Oh yeah. Kind of.
Now we've got a kinase again, Tori. Because what does a kinase do?
It
Transfer.
Transfers what?
Is your name Tori?
A phosphate group. What does it transfer a phosphate group from?
from
Yo, sweet Tori.
ATP to what?
to the
To this fructose 6-phosphate. Phosphofructokinase. Gosh, if that's not the best name ever for an enzyme, I don't know what
It
is.
doesn't look like English.
I know, but it is. It's elegant. Alright, now this is where it gets a little interesting. Because this next reaction is going to split our fructose 1,6-bisphosphate into 2 3-carbon molecules. One of those is going to be G3P. Okay, so this next enzyme splits this into 2 molecules. One of them is D3P. The other one will abbreviate DAP, or DAP.
Is that it?
Bro.
For that, like in between the tap and
What's that? I'm sorry?
is that it for like in between that
Yes.
that part?
Yes. And the enzyme that catalyzes this is aldolase.
Oh, that's so much better.
That was fine.
Okay? Notice I put the DAP here, because the G3P, it's already done. It's already ready to go. Right? The G3P, it's ready to go, but that DAP's got to go. This is ready, this one's not. This one's ready, this one's not. Which is why this is under the arrow. Man, the way I draw these things, it's enlightening. I don't think you appreciate that what I'm doing on this board is informing my own understanding, let alone yours. Gosh, there's some magic happening right now. Okay, so G3P, that's good to go, right?
Yeah.
But the DAP, that's not good to go. We need an enzyme that's going to convert the DAP into a second molecule of G3P. And that enzyme is called this. Triose phosphate isomerase.
That's a long one.
Yeah, because DAP is an isomer of G3P. DAP is an isomer of G3P. So we have an enzyme, triose phosphate, because now it's not a hexose, a 6-carbon sugar, it's a triose, a 3-carbon sugar. Triose phosphate isomerase to convert DAP into what? G3P. And now steps 1 through 5, they're done. Right? And we're ready to go with 6 through 10. And we've invested 2 ATP. We better get a return on our investment.
Yeah.
But I've already given you, we've already done our summary of glycolysis. So you already know we're going to get 4 ATP back. We invest 2, we get 4 back. We've doubled our investment. That's wonderful.
That is wonderful.
Keeping in mind that this happens literally hundreds of millions of times every second in your cell until you exhaust your glucose, you're getting a lot of return on your investment already.
You're right.
But then when you do the oxidative phosphorylation, we don't get 4 ATP for the 2 we invest, we get 32 to 34.
That's a lot of ATP.
We actually get 34 to 36 for the 2 you invest for a net of 32 to 34. So now you're not just doubling your investment. I don't even know what you would call that. It's like a 3,200% return on your investment. But already double. Have any of you ever seen how much money you would have if you started with a penny and you doubled it every day for a month? Have any of you ever done that in one of your math classes? You'd have about $5.5 million at the end of that month.
At the end of the month?
At the end of the month, if you started with 1 penny and it doubled every day for 30 days.
Somebody should do that and donate it.
Wait, is
And then 16, and then 32.
So you do 2, because you do 2 to the 29th power, right? Because that first day is just going to get you from 1 to 2, right? You start with 1 penny, you double it, now you've got 2 pennies. But then the next 29 days, you do 2 to the 29th power. And Kyle, go ahead and run that, and I'm gonna see if I remember correctly, and I'm gonna guess it's 5.3 million. But it's actually gonna be 530 million, but that's gonna be in pennies. Then we gotta divide it by 100 to figure out what that is in dollars.
I don't know if I believe this.
2 to the 29th power. Give it to me,
I
Kyle.
went like 10
Somebody
days
else do
sober.
that. I don't know. This is too
Give it to me.
Just raise it to 29.
Literally.
2 to the 29th power.
where's the carrot?
Where's
XY, or a caret. Does it have X to the Y?
I can't find it.
2 to the 29th. Is it 530 million?
Yeah, it's 5368.
Oh, so 536 million? And then so you divide that by 100, right? Because there are 100 pennies in a dollar. Do you know
And
that?
you get-
Do you know what a penny is? You seen a penny?
You get 536 million.
No, so then if you divide that by 100, you get $5.3 million.
$5,360,709.
So if I give you a penny on January 1st, and you invested that in day trading,
Hold on.
and every day you doubled your investment at the end of 1 month, not even a full month because January's got 31 days, on January 31st, you'd have $5.3 million. $5.36 million. Okay? So even just doubling our investment, that's a big deal. Do you agree?
Yeah.
That's a big deal. But getting a 3,200% return on your investment, that's a real big deal. Okay, now let's do steps. Let's do steps 6 through 10. How about we?
What?
It takes a week to get to $1 though.
I know, but then what? But then once you get there, it starts
Going fast.
It just starts really going. All right. I'm trying to remember the acronym for the next one. BPG. Okay. All right. So step 6 converts 2 molecules of G3P to 2 molecules of BPA. Or BPG.
Which one is it?
Either one. I mean, when you abbreviate something, there are multiple ways that you can abbreviate it. So we'll just say or. No, I'm not going to do that. That's confusing. We'll just call it BPA. But BPA, that's not, people don't like that, right? Because BPA is one of the things that can show up in plastics. That's a carcinogen. So, anyways, but that's what I'm putting. Sometimes it's abbreviated BPG. We've not got any return on our investment yet, but the enzyme that carries this out is called triose phosphate kinase.
Wait.
Yes, kinase. That means we're gonna need G, right?
No,
Is it transfers and phosphate?
this wasn't yet. I told you something wrong. Triose phosphate, this is dehydrogenase. Well, I already owe you.
Yeah, that's like.
You're supposed to give me a list of something you want. Not a list, just one item, yeah.
You know we forgot
For the AP exam, maybe not. Yeah. So here we have triose phosphate dehydrogenase. So I know part of this enzyme's written over there, but listen, shh. I have another enzyme name that I need you to see and always think something. So triose phosphate dehydrogenase. Triose phosphate dehydrogenase. Anytime you see a dehydrogenase, this is an enzyme that facilitates a redox reaction, an oxidation reduction. Because what's going to happen here is we have another reaction that goes along with this one. Let me give myself some space.
Okay, what does it do?
And we convert NAD plus to NADH.
Oh, that's sweet.
So we already knew that that was one of our products of glycolysis, right? NAD plus to make NADH. 2 molecules of NADH, right? Are products of glycolysis. Well, if we have 2 G3P and each one makes 1, how many do we make? If we have 2 G3P and each one makes 1 NADH, how many do we have? We have 2. We've accounted for the 2 NADH that we're going to make as a result of glycolysis. And then these are going to go give their electrons where? Either to the electron transport chain, if it's aerobic, or to where? If we're going to do fermentation, where are they going to give its electrons? To pyruvate.
Yeah.
Right? To form lactate. All right. All right. Now let's do this. Okay, now step 7. We convert 2 molecules of BPA to 2 molecules of PGA. What is it? PGA is the
Professional Golf Association.
Professional Golf Association.
That's
Okay.
the most boring professional association that there is.
But I actually left off part of the name. So we've got 2 molecules of 3 PGA.
I'd rather watch NASCAR than
Professional
NASCAR.
Golf
Yeah.
Association.
Alright, so in step 7. Yeah, so we make 2 molecules of 3 PGA.
What is
And
3
he-
PG? Sorry.
It's 3 phosphoglyceraldehyde is what it stands for, but I'm just giving you abbreviations at this point. So this is carried out by an enzyme that's called triose glyceromutase, or sometimes called phosphoglyceromutase.
Oh my goodness. These names just.
I know, they're wonderful. And here we get an ATP. But since we're doing each of these reactions twice, we get actually 2 ATP here. Alright, every one of these reactions we get to do twice because we started with 2 G3P. Gosh, this is... I don't know if we're going to have time to do Krebs cycle 2.0.
There's just too much good stuff.
I know. I know. And I gave you the wrong enzyme name. Oh my goodness. Oh my.
The whole thing?
The whole thing.
Oh my gosh.
I know. Gosh, it's just unraveling. My whole life.
I've never used this, you might have to like.
The owner of a great.
If we're transferring an if we're making ATP, what are we transferring, Tori? We're transferring, right? It's got to end in kinase because we're transferring what? A phosphate group. So the end of this enzyme is kinase. I should have known better. And this is phosphoglycero. Oh, I left the O off. Phosphoglycerokinase.
Oh, you switched it again? So I have to erase all that?
Yeah, all of it.
All of it.
All of it. This 2.0 is not going well for me.
It's one of those days. Everybody has those days.
No, it's okay. It's not gonna. I got it all. I got it all secured now. All right. So that's step 7. We've got now the 2 ATP we invested. We've got back, right? And now we just need to find those 2 extras. So for here, and now this is step 8. We're gonna go from 2 molecules of 3 PGA to 2 molecules of 2 PGA. Is it getting smaller? It's just changing chemically. What do you mean by smaller? Is the molecule getting smaller? No, it's just, this is referring to which carbon the phosphate is on. And so this one is on carbon 3, then it moves it over to carbon 2. And this enzyme is called phosphoglyceromutase, or phosphoglycerate mutase, phosphoglyceromutase. We're almost there.
One more.
We have 2 more.
Yeah.
2 more reactions.
Well, thing is, yeah. We already know the outcome of the second.
Step 9 produces PEP. And is catalyzed by a reaction called enolase, or catalyzed not by a reaction, by an enzyme called enolase.
Oh, it's a shorty.
I mean, compared to the others. And then what have we not accounted for yet? The other 2 ATPs, so they better come here, and they do, 2 more ATP. And if we're going to transfer phosphate groups from PEP to ADP, what kind of an enzyme has to do that? Tori?
Kinase.
A kinase, and this is called pyruvate kinase. And that's it. Now that's all correct.
I feel very relieved and educated.
You received the education.
And so Michelle asked a question. Do you need to know all of this? And I will tell you that for the AP exam, the answer to that is maybe, maybe not. Maybe, maybe not.
Safe and sorry.
Which from now on, a significant portion of our exams are going to be made up of old AP exams. And so if the answer is maybe, maybe not, you might find some questions.
You might find out soon.
Now, knowing the big picture, what we did initially when we went through glycolysis, Krebs cycle, oxidative phosphorylation, in kind of like a 30,000 feet approach, that's where you really need to focus. But knowing these details it's going to be helpful, especially knowing where we invest the ATP and where we get it back. Now I want to ask you a couple of questions. So everybody take a look at this. Take a look up here. And we talked about something when we were talking about just enzymes in general from chapter 8. And I told you that enzymes can be inhibited, right? And I told you that they're usually inhibited by the products of the reactions. Do you remember talking about that? And then I asked you, why on earth would a cell want to inhibit an enzyme from functioning? Do you remember the answer to that? To slow down a process. So what you find here is pyruvate, which is the end product of this 10-step reaction, actually inhibits one of the enzymes in the process to slow this down. So we look at pyruvate, and I'm going to tell you this is an inhibitor for one of these enzymes. And I want you, taking a look up here, I want you to guess, give me an educated guess as to which enzyme do you think is inhibited by pyruvate and why. Inhibited means it prevents it from functioning. And it's not a competitive inhibitor, meaning it doesn't compete with the enzyme for its substrate. It's an allosteric inhibitor. Okay? It bonds somewhere else and shuts it down entirely. It's like an off switch. So pyruvate is an off switch for one of these 10 enzymes. Which one do you think it is? Rick, I saw your hand.
I was gonna say PEP.
It is not. Well, PEP's not an enzyme. PEP's a substrate.
Oh,
So you would have to, you think it's going to be an inhibitor for pyruvate kinase? Okay. So if it inhibits this, it would go all the way through this process. It would invest 2, it would get 2 back out, and then it would just build up PEP. Right?
Yeah.
Okay, so, okay, we've got to vote for that. Anybody else have any votes? I want to get all of our proposals on the table before we come to a vote. Mark, do you have an enzyme that you think it inhibits?
NADH.
So NADH is it's not an enzyme, but this would be the enzyme that facilitates that. So you're voting for trials phosphate dehydrogenase? Okay, so we'll go Lydia, then Trinity, then Emma. Lydia. Which one? This one? Phosphoglyceromutase? Okay, Trinity.
I was going to say phosphoglucose.
Oh, that was the same as Lydia, right? Phosphoglucomutase? Is that what she said?
I'm talking about the one on the glucose side.
Oh, this one right here? Phosphoglucomutase? So you're going back towards the beginning of that. I like that. Emma.
I think triose phosphate isomerase.
Triose phosphate isomerase. Any others? Kyle. Hexokinase. So if you inhibited hexokinase, that's really nice, right? Because then you can prevent any of it from happening. It's not right, but it would be a really nice place to inhibit. So pyruvate acts as an allosteric inhibitor for this enzyme here.
I was really.
You were the closest. So pyruvate is an allosteric inhibitor for phosphofructokinase or phosphofructokinase. So it prevents the cell from investing a second ATP in this process if it already has enough pyruvate that can go and do the Krebs cycle.
Oh, so like a works.
Yeah, so it prevents the cell from investing more until it's ready to use it. But why wouldn't it inhibit it here?
Because you gotta see.
Because here you're investing 1. What controls which direction water moves?
It always moves
Oh,
down.
good.
Whoa.
The concentration.
Yeah, so water moves to where it's less concentrated. Where is water less concentrated?
Downhill.
Where
Yes,
there's
downhill.
more solute.
Where there's more solute, right? Total solute, doesn't matter what it is. Wherever there's more solute, there's less water, yes?
Yes.
But where do other materials move? Still down their concentration gradient. But now it only matters for that material, right? So if you have excess sodium outside of the cell, where is sodium going to want to move? If there's more sodium outside than inside, it's going to want to move inside, right?
Yeah.
Why would the cell want to do this reaction, even if it's got plenty of pyruvate and it's not going to go through glycolysis? Why would it still want to do this reaction here? Are glucose and glucose 6-phosphate the same thing? They're not. They have different names, right?
Yes.
So if you can immediately convert all glucose that comes into the cell into glucose 6-phosphate, what do you have 0 of inside of the cell? No, you have phosphate there. You have 0 glucose, right? If every time a glucose molecule comes into the cell, it's immediately converted into glucose 6-phosphate. What do you have inside of the cell?
Glucose.
0 glucose. Which means which direction is glucose always going to move?
Outside the cell.
No, if there's 0 inside of the
inside.
cell, it's always going to be less inside of the cell. And so the cell still wants to carry out this reaction to still encourage glucose to move inside. So it can build up a store of glucose for when the pyruvate gets used up and it starts going through this process again.
That's pretty nifty.
Yeah, that's pretty nifty. So it will continue to invest that 1 ATP to create a situation in which glucose is always going to flow into the cell.
Like the
So it can store up food for when it's going to need it.
It's like
Okay? So again, pyruvate is an allosteric inhibitor for phosphofructokinase. Prevent the cell from investing a second ATP. Okay? Does that make sense?
Yeah.
Are there any questions here? We're going to have to take our discussions of our 2.0s into Wednesday before we start our discussion of photosynthesis. Which is a little sad. But we're going to approach photosynthesis the same way we did cellular respiration, where we're going to go through it in like a summary, and then we'll go into it in more detail. Okay? Are there any questions on glycolysis, on any of these enzymes, on why on earth I gave you wrong information for the second consecutive class? Nothing? Yeah, Michelle.
Could you repeat what does
What's going on here?
Yeah.
So phosphofructokinase is an enzyme that catalyzes the reaction of adding a second phosphate group onto this to form fructose 1,6-bisphosphate. So that's one thing this enzyme does. But the reason I drew a box around it is because this enzyme is inhibited by pyruvate. So if the cell has gone through glycolysis so many times that it can't get pyruvate where? Where does pyruvate need to go to finish aerobic respiration? Because this is all happening in the cytosol, right? In that space, glycolysis happens in the cytosol, but everything else happens where? Inside of the mitochondria. So part of it happens in the matrix, right? Pyruvate oxidation and the Krebs cycle happen in the matrix all the way inside the mitochondrion, and then the electron transport chains on that inner mitochondrial membrane. Do you remember it? Is it coming back? I'm just so bad, right? You should remember better. I'll teach better. Okay. And so if you're going to finish this process and not do fermentation, pyruvate has to get into the mitochondria. And that's why you can't carry out those without oxygen, because oxygen provides a way to release enough energy by electrons falling down to actively pump pyruvate into the mitochondria. Okay, but if you can, and pyruvate is building up in the cytosol, the cell needs to shut this process down. So you don't just keep building up pyruvate, because then it becomes difficult for the cell to control which direction pyruvate moves. Right? Make sense? So pyruvate itself shuts this process down. The cell doesn't need to make anything to shut the process down. What's already being made shuts the process down. And where? Which step is inhibited by pyruvate? Step 3. Okay? Why does the cell still do step 1? Right, because it wants glucose to continue to want to flow inside the cell. Okay, so it does step 1 to make it to where basically at any given moment there is literally 0 glucose in the cell. Alright?
That's really interesting.
So fructose can enter this here, an alternative fuel, right? High fructose corn syrup. I don't know if you knew this or not, but high fructose corn syrup has fructose in it.
Never would have guessed.
It's just awesome. And it can enter in right here. There's an enzyme that will add a phosphate to carbon 6 of fructose, and then fructose will enter into here. Other sugars have to be converted into glucose and then can go through glycolysis. Okay? And then proteins can enter in right here. If they've got extra carbons on their R group, they can be converted into G3P and then can go through steps 6 through 10. Right? What else can come in right here? And often does.
Fat.
Yeah, which part of it? The glycerol backbone. That 3-carbon piece can be converted into G3P and then do steps 6 through 10. Look at that. We just did it. Yeah. Isn't this awesome? That's all I got. All right.
It's great.
Okay. I know it's Monday.
It's not your